Okay, here you'll see another example of solving a differential equation by power series. And truth is, the one I did in the last video is pretty easy as far as this goes. I think you'll find solving this one with the same kind of assumed solution is going to be a little bit harder. But how about this? I tell you what the solution looks like, and I'd like you to give me the first 6 terms of it. It turns out it's an infinite series, and we might not be able to write the whole thing down, but let's get the first 6 terms. That might be good enough. Okay, are there some guidelines? There are some basic guidelines. Here's what I would do if I was trying to do this. Make sure that every summation that you see in your equation under this assumed solution begins with the same order of x to the n. So they should all begin with a constant term, or they should all begin with a x to the first power term. If you have to make that happen, take terms away. Okay? If it's not like that already, take terms away from these as needed to make them all equal, at least in terms of their order. And then what? Well, then you combine them into a single expression. They should all involve this. They should all involve x to the n. That should match throughout them. And they should definitely all start at the same place. But combining them, you might have to shift the index to get a single expression, a single summation. Okay? All right, so bad news about solving this one is that's not enough room. So how about this? Let's take our assumed solution and see what it starts to look like in there. So if that's y, what's y double prime? Y double prime is the series from 2 to infinity n minus 1 a n x n minus 2, which is a power series all by itself. And what's x times y prime? Well, let's say you use rules of calculus and you find y prime, and then you multiply every term of this series by x. Here's what you'll get. Series from 1 to infinity n a n x to the n. Okay? So that's xy prime right there. That's not y prime, that's xy prime. All right. Plus 2y, well, that would be 2 times this. So I'm going to write it like this. So 2 multiplies every term of that series. So we'll say 2an x to the n going from 0 to infinity. Okay, so that's what we're going to solve. Now, what were the guidelines again? Guidelines were get each series, each individual part, to start with the same order term. In other words, what does this start with? Actually, the first term of that power series is constant, because you'll start off with x to the 0. The first term of this one is of order x to the first power. And then the first term of that one is actually constant too. So how about this? If we took out the constant terms and ran each of these onward from there, they would start where this one starts. So I'll put a note to myself that that's what I do. I'll take away out of this one that very first term, which is actually constant, which is 2a2 x to the 0. Okay, this one I'll leave alone, and this I'll also take out a constant. I'll take away what would be the first term of that series, which is 2a0 times x to the 0, which is constant. Now, we'll just take that out, and then we'll run the series from there. And here's what that'll look like. That one now starts at 3. Okay, but this doesn't change. Remember that one we didn't do anything with. So let's just write it as it is. And if we take away that obtained from the index of n being 0, well, now we would go to 1. And that would be the rest of it. Okay, 1 to infinity. 2 a2 x to the n. Now these aren't gone, it's just I took them out of the actual summations. They're still here. But how about we do this? Let's write them together, because they are both constants and they are both like terms. And that's the whole equation. Now what do I like about this? Well, okay, so there's, say this is a whole power series. That's the constant term. And where does this one and this one and this one start? First term there is of order x to the first power. Same here and same here. So you could think that was just one giant power series beginning with x and then x squared and x third and so on. So if I could just write that as one formula, I would know that that was 0, and then all coefficients of this, whatever it is 0. Okay. Well, so to do that, I need to combine them. I need them to start at the same place. Like, those start at 1, okay. And they also agree about their first term being of order x to the first power. This one starts at 3. So how about this? I just realized that I need it to be like that. And I try and figure out how to adjust this so that it's really the same series, but it just starts in agreement with these. Okay? So to be honest, I'll just wing it and see if I can get it to work. So that would be 3 times 2, and if I start with 1, that's 3 times 2. And then these match, so I get like so. And then this is now going to be x to the n, and that's the same thing. Okay? So let's do this. Let's say, all right, I'm not going to rewrite that whole equation down, but I'll tell you that I shifted the index there. Now look, they all start at 1. It's like one summation can apply to all these in one formula. Okay? So say now we combine that. Here's what this equation looks like now. I get a summation from 1 to infinity of what would be this plus that plus that. So let's write this way. Let's write n plus 2, n plus 1, a n plus 2, okay, plus n a n plus 2a2. Oh, sorry. I made a mistake there. That was supposed to be a sub n the whole time. All right, anyway, so 2an. So make sure you note that correction. You probably already noticed it, though. All right, and, oh, what about the x to, what about that? Wouldn't that x to the n be common to every single term? So we do this. So that just signifies that first term here is of order x to the first power, and then there's the coefficient. Second term x to the second power, and whatever that is the coefficient there. Let's not forget that this starts of order x to the first power, but the first term of this entire power series is actually constant. So we're going to put in the 2a2 plus 2a naught. Okay. Now let's see what we can say about that. I have a power series equal to 0. Every term is 0. So I could say this. I could say 2a2 is equal to negative 2a naught if I wanted to. Or it turns out a2 is the opposite of a naught. What else? Well, the coefficient of every single term here would have to also be 0. So let's say we got to work this out. N plus 2, n plus 1, an plus 2. Let's say I'm setting that entire coefficient to 0. It's going to look like minus an times n plus 2. Okay, and I'd like to, in general, solve for the later terms in terms of the earlier terms. So an plus 2 would be negative an over n plus 1. And what's that true for? N is 1 to infinity. And let's just say like that. I hadn't mentioned it in the other video, but that's an important thing to get when you're using this method. It's called the recurrence relation. Okay, it's just something that says how you find later terms in terms of earlier terms. Okay, all right. Now, so let's see what we can get out of this. I'd like to write a solution, okay, at some point, and I'll need to know the coefficients. So I know that, but let's see where we can get from this. Let's start from 1. What's it say? A sub 3 is negative a1 over 2. Okay, and there's not much else I can say about it besides that. What else? A sub 4 is negative a2 over, so I'm putting in 2, so 3. Okay, what else? A sub 5, negative a sub 3 over 4, but I know what a sub 3 is. So say you make use of the fact that that's got to be negative a1 over 2. Then that would actually make this positive a1 over 8. Okay. Now we can keep going, but I think that this is probably enough. Let's see. Where was the original question? The original question was, you assume the answer takes that form, which it does. Find the first 6 terms. I think we might be able to do that. So let's try to write down. There it is. What do you know about the constant so far? The a sub n. So here's the general solution. Okay, so it would be that y was a naught plus a1x. And what are we going to say from there? We happen to know that a2 is negative a naught. Okay, so where I would write a2x squared, because that's what that is. All right, negative a naught x squared. Okay, what would the next term be? Well, I mean, what is it? That's what we think the answer is. So it'd be a sub 3 x to the third power. What do we know about a sub 3? Oh, it's negative a1 over 2. Okay, so let's say this. Let's say negative a1 over 2 x to the third power. So I got 1, 2, 3, 4 terms, and I wanted 6. So I'll keep going. What do we got from here? I would say next a4 x to the 4th, but I found a4 to be like that. So we'll say negative a2 over 4. Sorry, 3. X to the 4th. Okay, and then my last one, if I was going to write the first 6 terms of the answer, would be a5 x to the 5th power. And I found that a5 is positive a1 over 8. So let's say here's our last one. a1 over 8 x to the 5th power. Now the series is infinite, you know, what the true answer is. But for the first 6 terms, there you have it. So let's see. Okay, so I was writing this down and I realized something. Remember, we want to give the answer in terms of just two unknown constants, a0 and a1. And I did find that a sub 4 was negative a2 over 3, but what I should have done is tell you that I know a sub 2. A sub 2 is negative a0. So what I would really need to say is negative a0 right there, which would be just a0 over 3. Okay. All right, so that's what I noticed about this. It's got a0, a1x, a0, x squared, a1 over 2, and then it's got this other thing, a2 in it. So I can't have that. So here goes. To give you my general solution in terms of just two unknown constants, which is what we normally do when we solve differential equations and give the general solution, I would get this. But then for that one, the a2 over 3, I'd really want to say a0 over 3, and it's positive. Okay, and then I don't have a problem with that one because my general solution has just two unknown constants, a0 and a1. So then my last term that I'm going to give is like so. So there it is. I overlooked that when I wrote it down, but I realized it, and now you see it. That's the form that you want the solution to take.